Chromatographic analysis, softening of hard water, the cleansing action of soaps, and purification of water are all surface-mediated chemical processes. In these examples, the reactions occur at the surface. The branch of chemistry that deals with the study of the phenomena that occurs on the surface or interface, that is, at the boundary separating two bulk phases, is known as surface chemistry. An interface is a surface that forms a common boundary between two different phases, such as an insoluble solid and a liquid, two immiscible liquids, or a liquid and an insoluble gas. The two bulk phases refer to the pure compounds or solutions involved in the reaction. The interface is represented by putting a hyphen or slash between the two bulk phases involved. For example, solid-liquid or solid/liquid. Surface chemistry is an important branch of chemistry as a number of phenomena like dissolution, crystallization, corrosion, heterogeneous catalysis, and electrode processes occur at an interface. Let us consider two molecules, one present in the bulk and the other on the surface of the liquid phase. The situation for the molecule on the surface of the liquid is different from the one in the bulk of the liquid. The molecule in the bulk experiences a balanced force of attraction from all directions. However, the molecule on the surface is surrounded by liquid molecules of the same phase and also by fewer molecules from the gaseous phase. As a result, the molecule lying at the surface experiences an unbalanced force or some net inward force of attraction. Similar inward forces of attraction exist at the surface of solids. If you put solid charcoal in a closed vessel containing oxygen, you observe that oxygen molecules are attracted to the solid surface of charcoal. As a result, the concentration of the gas on the surface of the solid increases. The same reaction occurs if a liquid put into a closed vessel containing gas. The gas molecules will accumulate on the surface of the liquid. This phenomenon of attracting and retaining the molecules of a substance on the surface of a solid or liquid, resulting in a higher concentration of the molecules on the surface, is known as adsorption. The substance on the surface of which adsorption takes place is called the adsorbent, while the substance thus adsorbed is called the adsorbate. In the example that we just saw, the molecules of oxygen are the adsorbate, while the solid charcoal is the adsorbent. The reverse process, that is, the removal of the adsorbed substance from the surface, is called desorption. It can be brought about by heating or by reducing the pressure. The adsorption of a gas on the surface of a metal is called occlusion. For example, hydrogen is adsorbed on the surface of nickel or palladium. It is important to note that adsorption is a surface phenomenon. Hence, greater the surface area of the adsorbent, greater is the extent of adsorption. Thus, finely divided metals and substances with porous structure are good adsorbents as they provide large surface area. Charcoal, silica gel, alumina gel, and clay act as excellent adsorbents. Let's look at some examples of adsorption. While clarifying sugar, an aqueous solution of raw sugar is passed over beds of animal charcoal. The animal charcoal absorbs the undesirable colors, and a colorless sugar solution is obtained. When delicate electronic equipment is stored, silica gel is used as a dehumidizer, since it makes the air dry by absorbing the water molecules present in it. Let's look at one more example. Add some activated animal charcoal to a dilute solution of an organic dye, methylene blue. Stir the solution thoroughly and then filter it. You will find that the filtrate thus obtained is colorless. This is due to the absorption of the dye on the surface of the animal charcoal. It is very important to note that adsorption and absorption are two different phenomena. Let's look at how they are different. The term adsorption refers to the attraction and retention of the molecules of a substance only on the surface of a solid or liquid, while absorption refers to the passing of a substance through the surface into the bulk of a solid or liquid. Adsorption is a surface phenomenon, whereas absorption is a bulk phenomenon, and the substance is uniformly distributed throughout the bulk. Let us understand this difference through an example. If a piece of chalk is dipped in a solution of ink and then broken, it is found that the actual pigment, the ink, is present only on the surface of the chalk and has not moved into the bulk of the solid. However, the solvent in which the pigment was present has uniformly passed into the bulk of the solid. Thus, the color component of the ink has undergone adsorption, while the solvent has been absorbed by the chalk. Another example is the action of water vapor. Water vapor adheres to the surface of silica gel. This is an example of adsorption, since the molecules are retained on the surface of the adsorbent. However, if we place calcium chloride in a closed vessel containing water vapor, calcium chloride absorbs water vapor and forms hydrated calcium chloride. This is an example of absorption, because water passes through the solid surface of calcium chloride. Sometimes, adsorption may be followed by the dissolution of the adsorbate in the adsorbent. This means that first, the material appears on the surface of the adsorbent and then passes into its bulk. When the two processes occur simultaneously, it is known as sorption. Dyeing fiber is an example of sorption. Dyes get absorbed as well as absorbed on cotton fibers. Let us now look at the thermodynamic aspect of adsorption. Adsorption is accompanied by a decrease in the residual forces of the surface. This implies that some energy is released when the molecules of the adsorbate get attracted to the surface of the adsorbent. That is, the change in enthalpy, delta H, is negative for the process. Also, the degree of freedom of the adsorbate decreases upon adsorption, which means that the change in entropy, delta S, is also negative for the process. We know that for any thermodynamic process to be spontaneous, the Gibbs free energy change, delta G, must be negative. The Gibbs equation is delta G is equal to delta H minus T delta S. So, delta G can be negative if delta H is sufficiently negative, since minus T delta S is positive for the process of adsorption. when delta H becomes equal to T delta S, or when delta G becomes 0, the adsorbate and the surface reach a state of dynamic equilibrium. You know that the accumulation of molecular species on the surface of a solid or liquid, resulting in a higher concentration of the molecules on the surface, is known as adsorption. Adsorption of gases on solids can be of two types: physical adsorption and chemical adsorption. Let us discuss physical adsorption first. When gas molecules or atoms are held to the surface of a solid by weak van der Waals forces, then it is called physical adsorption. Physical adsorption is also known as physisorption or van der Waals adsorption. Let's look at an example. In the adsorption of dihydrogen on the surface of finely divided platinum, hydrogen molecules are first attracted towards the surface of platinum by weak van der Waals forces, and then adsorbed due to the presence of unbalanced attractive forces or free valencies on the metal surface. This is physical adsorption. Here, platinum is the adsorbent and dihydrogen molecules the adsorbate. Note that there is no chemical bonding between the adsorbent and the adsorbate. Thus, we can also say that physical adsorption occurs when a gas accumulates on the surface of a solid by van der Waals forces without the formation of a chemical bond between the adsorbate and the adsorbent. Now let us discuss chemical adsorption. Chemical adsorption or chemisorption is defined as the phenomenon that occurs when gas molecules or atoms are held to the surface of a solid by chemical bonds. In the example of dihydrogen and platinum, on increasing the temperature, the adsorbed dihydrogen molecules on the surface of platinum dissociate into hydrogen atoms. These hydrogen atoms are held strongly by platinum through chemical bonds. The chemical bond can be ionic or covalent in nature. In some cases, both physical and chemical adsorption may take place at the same time, and it may not be possible to identify the types of adsorption. The basic characteristics of adsorption depend on the specificity of the adsorbent, nature of the adsorbate, reversibility of the process, enthalpy of adsorption, activation energy, layers of adsorption, and surface area of the adsorbent. Let us discuss how each of these characteristics affects physical and chemical adsorption. In physical adsorption, the surface of the solid or the adsorbent has no specific preference for any type of gas molecules or the adsorbate, because the van der Waals forces that act on the adsorbent and the adsorbate are universal. However, chemical adsorption is highly specific and will occur only when an ionic or covalent bonding is possible between the adsorbent and the adsorbate. Therefore, we can infer that while physical adsorption is not specific in nature, chemical adsorption is highly specific. The amount of gas adsorbed by the adsorbent also depends on the nature of the gas or the adsorbate. Different gases are absorbed to different extents by the same adsorbent at the same temperature. For example, at 288 Kelvin, 1 gram of charcoal absorbs 380 cc of sulfur dioxide, 16.2 cc of methane, and only 4.5 cc of hydrogen. The volumes of sulfur dioxide, methane, and hydrogen are reported at STP conditions. It may be seen from the critical temperature values that higher the critical temperature of a gas, the greater is the extent of absorption. This is because gases that can be easily liquefied have high critical temperatures and are more easily absorbed. This can be attributed to the fact that the van der Waals forces are strong in the range closer to the critical temperature of that gas. The critical temperature of a gas is defined as the temperature above which the gas cannot be liquefied, however high the pressure applied. It can be seen that the volume of the adsorbed gas increases as the critical temperature increases. The critical temperature of sulfur dioxide is 430 Kelvin, and hence it is adsorbed more on charcoal than methane and hydrogen, which have a critical temperature of 190 and 33 Kelvin respectively. In chemical adsorption, no correlation is seen between the amount of gas absorbed and the critical temperature of the gas, but adsorption depends on the chemical nature of the gas. The greater the reactivity of the adsorbate, the greater is the amount of adsorption. Therefore, we can infer that both physical and chemical adsorption depend on the nature of the adsorbate. Let us now discuss the reversible nature of the process. Like any other equilibrium, adsorption is a process involving true equilibrium, with adsorption on one side and desorption on the other. The two opposite processes include the adsorption of gas molecules on the surface of a solid and desorption of gas molecules from the surface of a solid into the gaseous phase. You know that adsorption is an exothermic process. The equilibrium can be represented as gas, the adsorbate, plus solid. The adsorbent is in equilibrium with the gas adsorbed on the solid plus heat. On applying Le Chatelier's principle, it can be seen that when we increase the pressure or decrease the temperature, the equilibrium shifts forward. That is, adsorption increases. Similarly, when we decrease the pressure or increase the temperature, the equilibrium shifts backwards. That is, adsorption decreases. In other words, desorption takes place. For example, 1 gram of charcoal absorbs about 10 cc of nitrogen at 273 Kelvin, 20 cc at 244 Kelvin, and 45 cc at 195 Kelvin. It is observed that adsorption of nitrogen on charcoal decreases with an increase in the temperature. Thus, we can say that physical adsorption is a reversible process due to the presence of weak van der Waals forces of attraction. However, during chemical adsorption, chemical bonds are formed between the adsorbate and the adsorbent molecules. For example, when oxygen is chemically adsorbed on carbon, To reverse this process, there is a need to free the adsorbed gas. However, the reverse process releases carbon monoxide or carbon dioxide instead of oxygen. Hence, chemical adsorption is irreversible in nature. Therefore, we can conclude that while physical adsorption is a reversible process, chemical adsorption is irreversible. Next, let us discuss the enthalpy change associated with physical and chemical adsorption. In physical adsorption, since the van der Waals forces of attraction are weak, the heat evolved or the enthalpy of adsorption is very little, around 20 to 40 kilojoules per mole. Chemical adsorption is also an exothermic process. However, in chemical adsorption, surface compounds form, and the forces involved are similar to chemical bonds. Thus, a relatively high amount of heat is evolved, about 80 to 240 kilojoules per mole. Therefore, we see that the enthalpy of physical adsorption is low, whereas the enthalpy of chemical adsorption is very high. Let us now discuss the activation energy required for adsorption. Activation energy is the minimum energy required to convert reactants into the respective products. Physical adsorption involves only weak van der Waals forces and does not involve the formation of surface compounds or any chemical bonds. Therefore, it does not require activation energy. However, as chemical adsorption involves the formation of surface compounds, activation energy is required for the formation of chemical bonds between the adsorbent and the adsorbate. A gas may be physically adsorbed at low temperature, but chemisorbed at high temperature. During the adsorption of hydrogen on nickel at low temperatures, hydrogen is physically adsorbed on nickel. However, at high temperatures, hydrogen gets chemisorbed on the surface of nickel. In other words, an increase in the temperature supplies the necessary activation energy for the formation of surface compounds, and the process is called activated adsorption. We can therefore conclude that physical adsorption requires no appreciable activation energy, while chemical adsorption requires high activation energy. Let us look at the type of molecular layers that are formed during physical and chemical adsorption. Layers of gas molecules are adsorbed one over another by van der Waals forces in physical adsorption. That is why multimolecular layers are formed under high pressure in physical adsorption. In chemical adsorption, a chemical bond is formed with the molecules that come in direct contact with the surface of the adsorbent. Hence, only a unimolecular layer is formed in chemical adsorption. Therefore, multimolecular layers are formed in physical adsorption, but only a unimolecular layer is formed during chemical adsorption. Let us now look at the impact of the surface area of the adsorbent on physical and chemical adsorption. The greater the surface area, the greater is the adsorption. Therefore, substances with porous structures are good adsorbents. Charcoal is a good adsorbent as it has a porous structure. For both physical and chemical adsorption, the extent of adsorption increases with an increase in the surface area of the adsorbent. Let us first recall some details about adsorption. You already know that at a constant temperature, the adsorption of a gas increases with an increase in pressure. At a low temperature, the physical adsorption of a gas increases rapidly on increasing the pressure. On the other hand, at high temperatures, the increase in adsorption is relatively less. Let us learn more about the effect of pressure on the adsorption of a gas at a particular temperature. Adsorption is basically an equilibrium process. In order to understand the equilibrium process, consider an adsorbent and a gaseous adsorbate in a closed vessel, placed at a particular pressure P. It is observed that due to adsorption, the pressure of the gas decreases initially and becomes constant after some time. This indicates that a state of equilibrium has been attained. Once equilibrium is reached, the rate of adsorption becomes equal to the rate of desorption. The extent of adsorption, that is, the quantity of gas adsorbed per gram of the adsorbent, is expressed as X by M, where X is the mass of the gas adsorbed and M is the mass of the adsorbent. The variation in the amount of gas adsorbed by the adsorbent with variation in the pressure at constant temperature can be expressed by means of a curve. This curve, at constant temperature, is called the adsorption isotherm. Freundlich, in 1909, was the first to propose a mathematical relation for an adsorption isotherm. He gave an empirical relationship between the quantity of gas adsorbed by a unit mass of a solid adsorbent and pressure at a particular temperature. The relation can be expressed as X by M is equal to K multiplied by P to the power 1 by N, where X by M is the amount of gas adsorbed by a unit mass of the adsorbent, N and K are constants, and P is the pressure. This relationship is generally represented in the form of a curve and is known as the Freundlich adsorption isotherm. In this adsorption isotherm, X by M reaches its maximum value at point PS. In other words, the extent of adsorption is the highest at this point. It can be seen from the curve that even if the pressure is increased beyond PS, the extent of adsorption remains the same. This is called the saturation state, and PS is called the saturation pressure. The saturation state is observed when the adsorbate forms a uniform molecular layer on the surface of the adsorbent. If you look at the curve carefully, you will observe that at a low value of equilibrium pressure, part OA of the curve is nearly straight and sloping. Therefore, for part OA of the curve, the relationship between pressure and quantity adsorbed can be represented by the equation x by m is directly proportional to p to the power 1. Observe the curve beyond point B, that is, at a very high pressure. At a very high pressure, x by m is independent of the value of p. This is represented as x by m is proportional to p raised to the power 0. Let's now look at part AB of the curve. For this part of the curve, x by m lies between p to the power 0 and p to the power 1. In other words, in the intermediate range of pressure, x by m depends upon p raised to the power of 1 by n, where n is a positive integer. At a particular temperature, n and k depend upon the nature of the adsorbate and the adsorbent. Note here that 1 by n has a value between 0 and 1, and the probable range is 0.1 to 0.5. Now, when 1 by n is 0, x by m is constant, and it is in this part of the curve that adsorption is independent of pressure. On the other hand, when 1 by n is equal to 1, x by m is equal to kp, which means that x by m is directly proportional to p. In other words, adsorption varies directly with pressure in this part of the isotherm. If you compare the adsorption isotherms for a gas at different temperatures, you will observe that at a particular pressure, there is a decrease in physical adsorption with an increase in temperature. The Freundlich adsorption isotherm can be validated by taking the logarithm of the isotherm equation. Taking logarithm of both the sides, the equation becomes log x by m equal to log k plus 1 by n log p. This equation corresponds to the equation of a straight line y equal to mx plus c. So, we plot a graph between log x by m and log p. If it is a straight line, then we say that the Freundlich adsorption isotherm is valid. Otherwise not. Note here that the intercept on the y-axis is equal to log k, and the slope of the straight line gives the value 1 by n. It has been observed that adsorption from solutions follows generally the same principles as laid down for the adsorption of gases. Let's verify this with an experiment. Take a litmus solution and add charcoal to it, and then shake it thoroughly. You will observe that after some time the litmus solution turns colorless. This is because the dye of the litmus solution is adsorbed by the charcoal. Similarly, when activated charcoal is added to a solution of acetic acid in water, part of the acetic acid is adsorbed by the charcoal and the concentration of acetic acid in the solution decreases. The amount of acetic acid adsorbed per gram of charcoal depends upon the surface area of the adsorbent, the temperature of the solution, adsorbate concentration in the solution, the nature of the adsorbate and the adsorbent. Though the exact mechanism of adsorption from a solution is not known, some important observations have been made for adsorption in solution. Temperature plays a major role in determining the extent of adsorption. As the temperature increases, the extent of adsorption decreases. Secondly, the extent of adsorption increases with an increase in the surface area of the adsorbent. Charcoal, because of its highly porous nature, provides a large surface area, and hence is the most preferred adsorbent in industry and pharmacy. Thirdly, as the concentration of the solute, that is, the adsorbate, increases in the solution, the extent of adsorption increases. Lastly, the nature of the adsorbate and the adsorbent governs the extent of adsorption. That is, the nature of the bonding between the adsorbate and the adsorbent depends upon the species involved. Variation in the extent of adsorption with the concentration of the solute is usually represented by the Freundlich adsorption isotherm. The equation can be represented as x by m is equal to k multiplied by c to the power 1 by n, where x by m is the amount of solute adsorbed by a unit mass of the adsorbent, and c is the equilibrium concentration when absorption is complete. Taking logarithm of this equation, we get log x by m is equal to log k plus 1 by n of log c. This equation also corresponds to the equation of a straight line, y equal to mx plus c. If the graph between log x by m and log c is a straight line, then we say that the Freundlich adsorption isotherm for solutions is valid. The Freundlich adsorption isotherm for solutions can be tested experimentally too. Let us take the example of the adsorption of acetic acid on charcoal again. Take equal volumes of acetic acid of different molar concentrations in different flasks and add an equal amount of charcoal to each flask. Shake the contents in the flasks and keep for some time. The final concentration of acetic acid is determined by titrating the resulting solution against a standard solution of sodium hydroxide. From the difference in the initial and final concentrations, the value of x, the amount adsorbed, can be calculated. The results obtained from this experiment also support the hypothesis that the extent of adsorption increases with an increase in the concentration of the solute. The validity of the Freundlich adsorption isotherm can therefore be established. Adsorption plays an important role in all phenomena and processes where surface properties are essential. The phenomenon of adsorption finds very extensive applications in industry, research laboratories, and in everyday life. Some important applications of adsorption are production of high vacuum, gas masks, humidity control, clarification of sugar, chromatographic analysis, heterogeneous catalysis, adsorption indicators, separation of inert gases, froth flotation processes, and curing diseases. Let us discuss these applications one by one. We will first discuss production of high vacuum. A vessel that has already been evacuated by a vacuum pump may still contain traces of air. If a bulb of activated charcoal is connected to this vessel, the remaining traces of air get absorbed by the activated charcoal. This results in the production of a very high vacuum. Gas masks, used by miners in mines, provide protection from both particulate matter and poisonous gases. These are based on the phenomenon of adsorption. Gas masks contain activated charcoal or a mixture of adsorbents that preferentially adsorb large volumes of poisonous gases and thereby purify the air for breathing. Another application of adsorption is to control humidity in the air. Silica and aluminium gel are used to keep the relative humidity as low as possible. They adsorb moisture from the air, thereby preventing damage to electronic devices and musical instruments. Silica gel is also used as a means of preservation to control relative humidity in museums and libraries and exhibitions. An application of adsorption from solutions is the clarification of sugar. Animal charcoal is used to decolorize sugar solution since it adsorbs the coloring materials and carries them with it when separated from the solution, leaving behind a clear solution. The phenomenon of adsorption has provided chemists an excellent technique of separating various components of a mixture. This technique, known as chromatographic analysis, is used widely in analytical and industrial fields. Chromatographic analysis is based on the selective adsorption of certain substances from a solution by a particular solid adsorbent. Let us now discuss heterogeneous catalysis. Adsorption plays a very important part in the catalysis of gaseous reactions by solid surfaces. Let us see how heterogeneous catalysis works. According to the adsorption theory, gaseous reactants are absorbed on the surface of a solid catalyst. This increases the concentration of the reactant on the surface of the solid catalyst, thereby increasing the rate of reaction. The theory also explains the greater efficiency of the catalyst in a finely divided state. A majority of heterogeneous catalysts are solids. For example, iron is used as a catalyst in the manufacture of ammonia. The use of vanadium pentoxide in the manufacture of sulfuric acid by the contact process and of finely divided nickel in the hydrogenation of oils to fats are other excellent examples of heterogeneous catalysis. An important application of adsorption in the laboratory is an adsorption indicator. An adsorption indicator is a substance that is adsorbed along with a change in the color at or near the equivalence point of a titration. This finds use in precipitation titrations. For example, potassium bromide is easily titrated with silver nitrate using eosin as an indicator. Fluorescein is another dye that is used as an adsorption indicator. The phenomenon of adsorption is also used to separate inert gases. A mixture of inert gases like neon, helium, and argon gets separated because of the varying degrees of adsorption of the individual gases on coconut charcoal at different temperatures. The amount of adsorption of noble gases increases with an increase in the atomic mass and a decrease in the temperature. The froth flotation process of concentration of sulfide ores in metallurgy is also an adsorption phenomenon. The ore particles are adsorbed on the surface of the froth, while the gangue settles at the bottom of the tank. Adsorption plays a very important role in biological systems. One very important application of adsorption is in curing diseases. A number of drugs get adsorbed on the surface of germs in the human body. The germs are killed by the action of the drug and the disease is eliminated. Look at an example before you learn about catalysis. When potassium chlorate is heated strongly at 653 to 873 Kelvin, it decomposes slowly, giving potassium chloride and oxygen. The same reaction takes place at an accelerated rate and at a lower temperature of 473 to 633 Kelvin when manganese dioxide is added to the reactants. You will observe that manganese dioxide is not consumed in the reaction. That is, at the end of the reaction, manganese dioxide has the same mass and composition as at the initial stage. Here, manganese dioxide has facilitated the reaction without itself being consumed. The presence or addition of a foreign substance alters the rate of many chemical reactions. In 1935, Berzelius recognized these foreign substances as a new chemical force and called them catalysts. Thus, we can say that in the decomposition of potassium chlorate, manganese dioxide behaves as the catalyst. A catalyst is thus defined as a substance that alters the speed of a chemical reaction without itself being consumed in the process. This phenomenon is known as catalysis. Haber's process for the manufacture of ammonia is carried out in the presence of iron and molybdenum. Iron behaves as the catalyst in this reaction, while molybdenum enhances the activity of the iron catalyst. The substance that enhances the activity of a catalyst is called a catalytic promoter. In Haber's process, molybdenum acts as the catalytic promoter. The promoter increases the roughness of the catalytic surface, thereby increasing the free valencies or active sites. Promoters also aid the dispersion of the catalytic material. This results in an increase in adsorption. and thus the rate of reaction increases. There are certain substances that lower the activity of the catalyst. They are called catalytic poisons. Quinoline, sulfur, and arsenic are commonly used for poisoning the catalyst. For example, Lindlar's catalyst is poisoned with quinoline or lead acetate for carrying out the hydrogenation of an alkyne to an alkene. Otherwise, the reduction will go on to the alkane stage. Catalysis can be broadly divided into two types: homogeneous catalysis and heterogeneous catalysis. Let us first learn about homogeneous catalysis. Consider the oxidation of sulfur dioxide to sulfur trioxide in the presence of nitric oxide as the catalyst. As can be seen, the catalyst, nitric oxide, and the reactants, sulfur dioxide and oxygen, are all in the gaseous phase. A reaction where the catalyst and the reactants are in the same phase is called homogeneous catalysis. Homogeneous catalysts function in the same phase as that of the reactants. Consider the hydrolysis of sucrose solution in the presence of dilute sulfuric acid. The catalyst, dilute sulfuric acid, is in the same phase as that of the reactant sucrose, that is, in the solution phase. Therefore, this reaction is also an example of homogeneous catalysis. Let us now discuss heterogeneous catalysis. Consider the manufacture of ammonia by Haber's process. Both the reactants, nitrogen and hydrogen, are in the gaseous phase, and the catalyst, iron, is in the solid phase. A reaction where the catalyst involved in the reaction is in a different phase than that of the reactants is known as heterogeneous catalysis. And iron is an heterogeneous catalyst in Haber's process. Heterogeneous catalysts act in a different phase than that of the reactants. Most heterogeneous catalysts are solids that act on substrates in a liquid or gaseous reaction mixture. Let us consider another example, that of the hydrogenation of vegetable oils in the presence of finely divided nickel as the catalyst. In this reaction, the catalyst, nickel, is in the solid phase, and the reactant, vegetable oil, is in the liquid phase, while hydrogen is in the gaseous phase. Thus, nickel is a heterogeneous catalyst, and this is an example of heterogeneous catalysis. Diverse mechanisms of heterogeneous catalysis are known. We will discuss three theories of heterogeneous catalysis, namely, the old adsorption theory, the intermediate compound formation theory, and the modern adsorption theory. Let us first discuss the old adsorption theory. According to the old adsorption theory, the reactants in the gaseous phase and the solution phase are adsorbed at the active sites on the surface of the catalyst. This results in an increase in the concentration of the reactant molecules on the surface of the catalyst. As a result, the rate of reaction increases. The relative ease with which the product is separated from the surface of the catalyst helps a continuous chemical process to be initiated. Also, as adsorption is an exothermic process, the heat evolved in the reaction helps to speed it up. Let us now discuss the second theory of heterogeneous catalysis, the intermediate compound formation theory. According to the intermediate compound formation theory, the reactants A and B first combine with the catalyst C to form an intermediate complex. This intermediate complex is short-lived and decomposes to give the products, while the catalyst is regenerated. You already know that the presence of a catalyst provides an alternate path to the chemical reaction. A look at these curves shows that the activation energy of the catalytic path is much lower than the non-catalytic path. Also, the peak of the curve represents the intermediate complex. You can see that the intermediate complex formed with the catalyst has a much lower potential energy than the intermediate complex formed between the reactants in the absence of the catalyst. Now, as the energy barrier for the catalytic path is lower than the non-catalytic path, the rate of reaction increases in the presence of a catalyst. Thus, we see that the intermediate compound theory provides an alternative sequence of elementary steps to accomplish the desired chemical reaction. Let us now move on to the modern adsorption theory of heterogeneous catalysis. The modern adsorption theory is a combination of the old adsorption theory and the intermediate compound formation theory. This theory explains most examples of heterogeneous catalysis. According to the modern adsorption theory, free valencies are present on the surface of the solid catalyst. The catalysis process involves 5 steps. The first step involves diffusion of the reactant molecules towards the surface of the catalyst. The second step involves adsorption of the reactant molecules on the surface of the catalyst, followed by the formation of weak bonds with the catalyst due to the presence of free valencies. The third step involves a chemical reaction between the reactants and the catalyst, forming a complex that is essentially the product attached to the catalyst. The fourth step involves desorption of the product molecules from the surface of the catalyst as it lacks affinity for the catalyst surface, making the surface free and ready to interact with another reactant molecule. The last step involves diffusion of the product molecules away from the surface of the catalyst. The modern adsorption theory successfully explains that only a small quantity of the catalyst is sufficient for the reaction, as the catalyst is regenerated in the reaction, and that at the end of the reaction, the mass and the chemical composition of the catalyst remains unchanged. However, the main drawback of the modern adsorption theory is its inability to explain the action of catalytic promoters and catalytic poisons. From the earlier discussions, you are already aware that most heterogeneous catalysts are solids and that they act on the substrates in a liquid or gaseous reaction mixtures. These solid catalysts may be metals, metal oxides, metal sulfides, or clays. They may be used in their pure form or in the form of their mixtures. Further, they may be crystalline, microcrystalline, that is, in the form of fine particles, or amorphous. However, two important features that govern the choice of a solid catalyst for a particular reaction are activity and selectivity. Let us first discuss the activity of a catalyst. By activity of a catalyst, we refer to its capacity to increase the speed of a chemical reaction. Consider the chemical reaction between hydrogen and oxygen to form water. In the absence of any catalyst, hydrogen and oxygen do not combine, and therefore can be stored for an indefinite period. However, in the presence of platinum as a catalyst, they react rapidly to form water. Thus, the activity of a catalyst depends upon the extent of chemisorptions. The adsorption of the reactant molecules should not be so strong that their molecules become immobile, and further adsorption of reactant molecules is not possible. For hydrogenation reactions, it has been observed that the catalytic activity increases from group 5 to group 11. For example, the adsorption of hydrogen onto the surface of tungsten tends to be too strong, while its adsorption onto silver is too weak, making them both less useful as catalysts for hydrogenation as compared to nickel or platinum. Let's now look at the selectivity feature of a solid catalyst. Consider these chemical reactions of carbon monoxide and hydrogen in the presence of different catalysts. In the first reaction, carbon monoxide reacts with hydrogen in the presence of copper as the catalyst to form formaldehyde. In the second reaction, carbon monoxide reacts with hydrogen in the presence of nickel as the catalyst and forms methane and water vapor. In the third reaction, carbon monoxide reacts with hydrogen in the presence of copper and zinc oxide with chromium oxide as the catalyst to form methyl alcohol. We can see that carbon and hydrogen react to form different products in the presence of different catalysts. Thus, we can define the selectivity feature of a catalyst as its ability to direct the reaction to form a particular product or products, excluding others. A substance chosen as the catalyst for a reaction can act as a catalyst for that reaction only, and not for any other reaction. It means that a substance that acts as a catalyst in one reaction may fail to catalyze other reactions. This shows that catalysts are highly selective in nature. The role of catalysts is shifting more and more towards getting better selectivity to a desired product in a chemical reaction. Let us now learn about another important class of reaction, shape-selective catalysis. The catalytic reaction that depends upon the structure of the pores of a catalyst and the size of the reactant and product molecules is called shape-selective catalysis. An important category of compounds that have the ability to act as good shape-selective catalysts are zeolites. They are microporous crystalline solids and possess well-defined honeycomb-like structures. Chemically, zeolites are aluminosilicates with the general formula MX/N. AlO2X SiO2YZ H2O, where N is the charge on the metal ion, which is either sodium or potassium or calcium ion, and Z is the number of water molecules of hydration. In aluminosilicates, some silicon atoms in the tetrahedral structure of silicates are replaced by aluminium atoms, giving it an aluminium-oxygen-silicon type of framework, while the cations and water molecules are present within the pores. Zeolites are found in nature as well as are synthesized for catalytic selectivity. Before being used as catalysts, zeolites are heated in vacuum so that the water of hydration present in the cavities in the cage-like structure is lost and they become vacant. Thus, the shape and the size of the pores control the axis of the reactants and the products. In other words, the reaction taking place in a zeolite depends upon the shape and size of the reactant and product molecules, as well as the pores and cavities of the zeolite. It means that they are shape-selective catalysts. Because of their unique porous properties, zeolites find applications in a variety of processes. Zeolites are commonly used in water softening and purification, in synthesis of high-value pharmaceuticals, in petrochemical industries for cracking hydrocarbons, for isomerization, and in fuel synthesis. An important zeolite catalyst used in the petrochemical industry is ZSM5, which is a zeolite sieve of molecular porosity 5. ZSM5 converts alcohol directly into gasoline or petrol by dehydrating it, resulting in a mixture of hydrocarbons. All applications of zeolites are driven by environmental concerns, and they contribute significantly to a cleaner and safer environment. Before we actually begin our discussion, let us look at the journey of the food we eat. When we chew food in the mouth, the enzyme amylase works on starch, breaking a big sugar into smaller sugars. In the stomach, the food is exposed to acidic gastric juices that contain the enzyme pepsin, which splits protein molecules into simpler molecules. Further, pancreatic juices contain various enzymes that continue to break down proteins, sugars, and fats. By the time food moves into the small intestine, it has been broken down into tiny nutrients that the body can absorb and use for energy, repair, and growth. Thus, we see that all biological reactions are catalyzed by special catalysts called enzymes. Enzymes are, therefore, known as biochemical catalysts, and this phenomenon is known as biochemical catalysis. In the absence of enzymatic catalysts, most biochemical reactions would not occur under the mild temperature and pressure conditions that are compatible with life. Chemically, all enzymes are proteins of high molecular masses consisting of amino acids as the building blocks held together by peptide bonds. Enzymes are obtained mostly from living plants and animals. In 1969, an enzyme was synthesized for the first time in the laboratory. Enzymes form a colloidal solution in water. A colloid is a type of mixture in which one substance is dispersed evenly throughout another. Every enzyme has a functional name that classifies it in terms of the kind of reaction it catalyzes, or has a specific name that usually consists of a part of the name of the substrate molecule. A molecule that is acted upon by the enzyme is referred to as the substrate molecule. Let's take a look at some more enzyme-catalyzed reactions. In the hydrolysis of cane sugar, the enzyme invertase converts cane sugar or sucrose into glucose and fructose. In the enzyme-catalyzed reaction of conversion of glucose into ethyl alcohol, the enzyme zymase is used. Similarly, the conversion of starch into maltose is carried out with the enzyme diastase, which is extracted from malt. Another enzyme, maltase, converts maltose into glucose. All the enzymes, invertase, zymase, and maltase, are obtained from yeast. The decomposition of urea into ammonia and carbon dioxide is catalyzed by the enzyme urease. The source of urease is soybean. Milk is converted into curd by the enzyme lactobacilli, which is present in curd. Let's now study some fundamental characteristics of enzymes. Enzymes have high efficiency and high specificity. They are highly active under optimum temperature and under optimum pH. They show increased activity in the presence of enzyme activators and coenzymes, and a decreased activity under the influence of enzyme inhibitors and poisons. Let us study each characteristic in detail. We will first discuss about the efficiency feature of enzyme catalysts. Let us look at an example to see how enzymes are efficient in speeding up reactions. We know that a peptide or an amide bond is a very stable bond. The hydrolysis of an amide in the laboratory requires it to be heated with an alkali for a few hours. The proteins in our food contain peptide bonds. These proteins are easily hydrolyzed by different enzymes to individual amino acids in the stomach and the small intestine. Enzymes accelerate such reactions by over 1,000,000-fold. So, the reactions that would take years in the absence of catalysts can occur in a fraction of a second if catalyzed by the appropriate enzyme. An idea of the efficiency of enzymes can be had from the fact that in their absence, it would take 50 years to digest one single protein-rich meal. Thus, we conclude that enzymes are very efficient catalysts. They speed up reactions by lowering their activation energy. Let us now discuss another feature, high specificity. As we have seen some reactions just now, each enzyme catalyzes only one chemical reaction, which indicates that they are highly specific. Most industrial catalysts are responsible for more than one catalysis and are considered relatively non-specific. Enzymes are very different. Most enzyme molecules catalyze only one specific reaction, but in a phenomenally efficient manner. One enzyme molecule might be responsible for converting thousands of reactant molecules, called substrate molecules, into the product. Let us now discuss the effect of temperature on enzyme activity. Every enzyme has a temperature range of optimum activity. Outside that temperature range, the enzyme is rendered inactive. At a definite temperature, the rate of reaction reaches its peak. This is called the optimum temperature of the reaction. On either side of the optimum temperature curve, enzyme activity decreases. The optimum temperature range for enzymatic activity is 298 Kelvin to 310 Kelvin. The temperature of the human body, 310 Kelvin, is suitable for enzyme-catalyzed reactions. Another characteristic that affects enzyme activity is pH. Every enzyme has an optimum pH range, outside which its activity is inhibited. The rate of an enzyme-catalyzed reaction is maximum at a particular pH. This is called optimum pH. The optimum pH value lies between 5 and 7 on the pH scale. An important feature of enzymes is that their activities can be modulated, that is, increased or decreased. Let us now learn about enzyme activators and coenzymes. In the conversion of starch into glucose, the enzymes amylase shows high catalytic activity in the presence of sodium ions provided by sodium chloride. Activators are generally metal ions, such as sodium ion, manganese ion, copper ion, and cobalt ion. These metal ions form weak bonds with enzymes and increase their catalytic activity. Enzyme activity also increases in the presence of certain substances known as coenzymes. They are called coenzymes because they work together with enzymes to enhance reaction rates. Most coenzymes are derived from vitamins. It is important to note that coenzymes are the non-protein portion, while enzymes are proteins. The last characteristic of enzymes is the influence of inhibitors and poisons. Some substances slow down the activity of enzymes. These substances are called inhibitors or poisons. Many toxic substances owe their toxic properties to their ability to act as inhibitors to important enzymes that catalyze biochemical processes. Once an enzyme has been inhibited, the process that it catalyzes cannot take place. For example, cyanide poisoning is due to the cyanide ion competitively inhibiting the active site responsible for cellular respiration. Chemotherapeutic treatment of cancer utilizes the property that drugs behave as inhibitors to important enzymes responsible for the growth of tumors. Thus, we can say that the use of inhibitors can be for the benefit of mankind or its destruction. Let us now understand the mechanism of enzyme catalysis. The catalytic activity of enzymes involves the binding of their substrates to form an enzyme-substrate complex. The substrate binds to a specific region of the enzyme called the active site. These active sites are associated with the functional groups such as amines, carboxylic acid, hydroxide, and thiol. The binding of the substrate to the active site of an enzyme is a very specific interaction. Also, the shape of the active site of an enzyme is such that only a specific substrate can fit into it. Just as only a particular key can fit into a specific lock, only a specific substrate can fit into a particular enzyme. Hence, the mechanism is known as the lock and key mechanism. This specific binding leads to the formation of an enzyme-substrate complex. When bound to the active site, the substrate is converted into the product. Further, as the product molecules do not have any affinity for the enzyme surface, they leave the enzyme surface immediately. Thus, an enzyme-catalyzed reaction can be illustrated in two steps. The first step involves the formation of the activated enzyme-substrate complex. The second step is the decomposition of this activated enzyme-substrate complex to form the products. In order to procure the maximum yields of the product in the least time, chemical industries use catalysts to accelerate the rate of reactions. The commercial preparation of ammonia, sulfuric acid, and nitric acid are also based on the phenomenon of surface catalysis. Haber's process for the manufacture of ammonia uses iron as a catalyst and molybdenum as promoter. To strike a balance between the quantity and quality of the product, the process is carried out at 723 to 773 Kelvin temperature and 200 bar pressure. In the manufacture of nitric acid by Oswald's process, ammonia is converted into nitric oxide in the presence of platinum asbestos as a catalyst at a temperature of 573 Kelvin. In the contact process for the manufacture of sulfuric acid, platinized asbestos or vanadium pentoxide is used as a catalyst for the oxidation of sulfur dioxide to sulfur trioxide at a temperature of 673 to 723 Kelvin.